Ladies and gentlemen, welcome to the online conference Wastewater Management. It is the fifth event of the Sustainable Business and Circular Economy series. It is organized by the Nordic Chamber of Commerce in the Czech Republic in cooperation with the Masaryk Water Research Institute in Prague. This event is supported by the collaboration of embassies of Norway, Denmark, Sweden, Finland, Ireland as well. My name is Irina Jilková. I am professor at the University in Ústí nad Labem, and I have the pleasure and honor to guide and moderate this workshop. Our motto, as presented at the invitation, is that the water is local and global resource, a transport corridor and climate regulator. But it has become the end of the journey for many pollutants released to nature. So the issue of wastewater treatment is of key importance for us, for the whole society. I have the pleasure now to give the word to Mr. Tomáš Urban, the head director of the Water Research Institute, to introduce us more to the topic.
So, thank you for introduction. Dear ladies and gentlemen, I'm a pleasure to welcome you to today's seminar, which focuses on the wastewater management. Wastewater is an underestimated topic for most of the people, but at the same time, it affects quality of their lives. Wastewater compared to the drinking water is not spelled so often, is less visible, but it's slowly becoming a real problem and should get more attention. Wastewater is cross-connected with other problems we are facing these days. New pollutants, not easily removed by current wastewater treatment technologies, are of emerging concern, including certain veterinary and human pharmaceuticals, pesticides, antimicrobial disinfectants, flame retardants, detergents, metabolites, and microplastics. Their concentration certainly increases during the drought when wastewater becomes a large part of water in rivers or in surface water in general. When we speak about marine litter, then the sources can be generally correlated with the efficiency of solid waste management, but also wastewater management and wastewater treatment. United Nations study called Global Environment Outlook, which is known also as GO6, says that 80% of all wastewater produced globally is discharged into the environment without any treatment. Wastewater contaminated with human fecal matters as well as the pharmaceuticals and endocrine disruptors that are newly threatening human health and ecosystems. OECD stated that in Europe, it is connected to water treatment plants about 70 to 100% of population, certainly depending on the country, but it doesn't say anything about the efficiency of the treatment. It's worth to mention that sanitation and clean water belongs among Sustainable Development Goals, which is issued by OSN. Specifically, it's under number 6. I hope that today's presentations will give us some new ideas, what is possible to do with wastewater, especially with the urban one. Now I would give a word back to Mrs. Jilková, which would guide you through the rest of the presentations. Thank you.
Thank you, Mr. Urban. Thank you, Tomáš, for the introductory speech guiding us towards our topic. And now I will open the floor for Lucia Garvalová from the Water Research Institute for her speech about the COVID-19 detection in the water. You have the floor, Lucia.
Thank you very much. I would like to tell you a little bit more about the detection, and I hope you can see all my presentation. Detection of SARS-CoV-2 in wastewater in Czech Republic is a topic which we are dealing in our Water Research Institute from April last year, and I would like to give you a little bit more information about it. Experience with other viral diseases has shown that monitoring sewage for traces of pathogen enables effective surveillance of entire communities, providing a sensitive signal of whether a pathogen is present in the population or whether the transmission is increasing or decreasing. Researchers around the world are now pursuing the same approach for COVID-19 with the hope that wastewater data can supplement some new data for the surveillance of this pandemic. Wastewater monitoring has proved itself to be a very useful tool in several countries. For example, in the Netherlands, they are using wastewater data from over 300 sampling points right now, and they are using them in their dashboard. They are sending testing teams into areas with a higher prevalence of positive samples. Also, Italy has, for example, used older historical wastewater samples from December 2019 to prove that they had already COVID-19 circulating in their area more than a month before the first confirmed case. Here in Czech Republic, the first wastewater sampling took place in the spring of 2020. There are several advantages to building a wastewater monitoring system similar to the one in Netherlands. It is a cost-effective way to monitor a spread of the virus in a larger population. Thanks to this data, we can understand the prevalence of infections or the scale of the outbreak in the whole catchment area. And thanks to this, we could also protect more the vulnerable, the ones who are most likely to die from the infection. This data, together with the results from clinical testing, should give us a clear view on the state of the epidemic. And data from wastewater can show us a trend in which the pandemic is moving. So is the curve of infections increasing or decreasing, or are we seeing stagnating numbers? We can then identify our areas of concern, because we can see whether we should be more testing people more often in that area. We can monitor wastewater also and track the prevalence of the different viral variants on a larger scale. So there are several huge advantages of this approach in the pandemic. The objective of our project was to detect SARS-CoV-2 RNA in wastewater as one of the tools for an establishment of an early warning system, and to develop a methodology for the detection of selected microbial agents by PCR in wastewater. Our pilot monitoring started with the onset of the pandemic in 2020, and we were sponsored by an internal grant from our institution. Back then we started in April, and we were monitoring approximately 40 wastewater treatment plants till June 2020. In that time, we collected 137 samples, which were both grab and composite samples, mostly of untreated raw wastewater. As you can see on the map, we built a rather broad network of wastewater treatment plants in Czech Republic. And even though the infection rates at that time were really low, we were able to catch 20 positive samples in 11 different wastewater treatment plants. In our pilot project, 500 milliliters of wastewater were concentrated through direct flocculation using beef extract. Nucleic acid was isolated by Nuclisense Minimax system. And Eligene COVID reverse transcriptase kit was used for a real-time PCR analysis. Transmissible gastroenteritis coronavirus was used as a process control, and we were only evaluating whether a sample is positive or negative with the quantification cycle value under 40 being considered a positive samples. Back then, we were dealing with 3 different scenarios with our results. The one was absence of the virus in wastewater in locations where we knew that a positively tested person was actually registered. The second was when we got a positive wastewater sample in locations where no infected persons were reported at that time. And of course, the one which we were mostly expecting was positive samples in an area where people were tested positive for the virus. Here you could see on this graph an example of a wastewater treatment plant in which we had several samples that tested positive for SARS-CoV-2 RNA. And we also had the occurrence of positive infected individuals in the area. So this gave us hope, or based on this, we knew that this could actually work and that we could use this tool to monitor the spread of the virus better. Thanks to this, we are currently working on a project supported by the Security Research Program of the Czech Republic. This project started in January 2021 and will end in December 2022, but we have started the sampling process already in October 2020, since back then we were dealing with a rather huge second wave of infections in Czech Republic. Up until today, we have collected over 400 samples from 52 wastewater treatment plants. Our biggest aim was to develop a new methodology for the detection of selected microbiological agents by PCR in wastewater. And also during the course of the project, we were looking into new ways to optimize the sampling process of wastewater monitoring. Our new methodology had several advantages over the one used in the pilot project. For example, pH adjustment of the samples was not needed anymore, which is great because we did not contaminate our pH meter. Nucleic acid isolation was adapted for the needs of normal common laboratories. We are now using a 2-step reaction, so we are less prone to inhibition or false negative results. We have established an external control which could give us more precise results on the amount of SARS-CoV-2 in our samples. And the quantification is now based on the SARS-CoV-2 transcript, so we get better results. And we are very thankful that this method was developed in this project thanks to the cooperation with Veterinary Research Institute. On this graph, you can see the results from a wastewater treatment plant in Brno from our current project. And as you can see, the quantification process gives us better predictions, and we can see whether we have correlations between the infection rates and the viral loads in the wastewater. But since the best analytical methods won't give us any results if we don't do the sampling correctly, we were also looking into ways how to achieve or optimization of this process. If we want to sample for the monitoring of COVID-19, we have to first decide what we want from the sample. So do we want to have specific sampling on building levels, meaning, for example, schools, dormitories, hospitals, airports? Or do we want to have a huge city where we could better monitor in sewer lines rather than in a wastewater treatment plant? One possibility is also to work your way down, so from going from positive samples in a wastewater treatment plant and working our way down to building level and see where we have this cluster or where we have these infections. And in all these scenarios, it is important to consult the public health department and see what their needs are and see what they actually want to get from these results. Also, when dealing with technicalities of the COVID-19 sampling, we have to see what we want to get. Composite 24-hour samples have proven themselves to give a better picture of the population in the catchment area. However, in some sampling points, we only can get grab samples if it is possible. We were also looking into ways to adjust the sampling time better to achieve better results. Also, when dealing with composite samples, we should consider whether it is possible to get flow-based rather than time-based sampling. And if not, whether we should incorporate a correction constant in the evaluation of such samples, for example, based on the daily flow. During warmer season or in warmer regions, it is also important to see whether we can incorporate some cooling system during the sampling, since SARS-CoV-2 particles are sensitive to heat. Unluckily, it is not always possible to control the weather and to get the best results and best samples. In that case, we should always consider the possibility to normalize the data we get through some data correction. For example, standardize using some human biomarkers or chemical pharmaceutical markers. We in our project are using, for example, neopterin. Then we also want to collect wastewater data from daily flows, fecal indicator bacteria, etc. See whether we can get some correction, whether we see a spike in some data. And based on this, we can also refine some mathematical corrections in the evaluation of the data, see whether we could incorporate also things like temperature, rainfall, if we really can get the most specific results for that area. We were trying to achieve the best sampling by seeing when we should sample and not just sample 24-hour composite samples. So we had an experiment on several wastewater treatment plants back in March of 2021. And we were sampling on an hourly basis, and based on the microbial contamination and the chemical biomarkers, we could see that the biggest pollution came in during 10 a.m. and 9 p.m. And during that time, probably the most contamination and pollution was flowing in the wastewater treatment plant. This was back in times when people were still at home and working from home office, and the children didn't go to school. So of course, the behavior of people in the catchment area can change. But we decided back then that we will compare 24 hours composite samples with samples which took place from 5 a.m. till 11 p.m. And as you could see that we got way better results for the 18-hour composite samples, so from 5 a.m. to 11 p.m. than from the 24-hour composite samples, which are normally taken in wastewater treatment plants. Actually, in two cases, we only detected the viral RNA in samples which were 18-hour composite samples. And if we were sampling only the 24-hour composite samples, we would not get any viral RNA detection. Also, we were trying to compare whether it is possible, in case that we cannot use composite samples, on not even 24-hour composite samples, to use grab samples. So we had two wastewater treatment plants, one bigger, Brno, and a smaller in Břeclav. In Brno, we had 24-hour flow proportionate sampling, and in Břeclav we had time proportionate sampling. And as you can see, in Brno, which is a bigger city with flow proportionate sampling, the 24-hour composite samples gave us better results than the grab samples. But in Břeclav, where we also had the factor that the composite samples were only time proportionate and the city is smaller, so also the behavior might be different of the people in that area. The results from composite 24-hour samples and grab samples were rather similar. But what are our future goals and aims in our project and work? So we, of course, want to boost national and international cooperation, because without it, we won't be dealing with the pandemic, or we need to be dealing with the pandemic on an international level. We want to create a systematic network for monitoring wastewater for infection diseases spread. So not only when we actually have a problem. And actually, that would be our biggest goal, is to use artificial intelligence for early detection and prediction of the epidemic development through monitoring of wastewater. Since there are, as I already mentioned, many parameters which could influence the results, and we need to evaluate them better. And I would like to thank you all for your attention.
Lucia, thank you very much for your interesting presentation. As I see, we have no questions in the Slido. If I may raise a question regarding the acceptance of the method you have presented by the political representation. I mean, is there any interest at the Ministry of Health Management? They would use this method for the COVID pandemic management in the next future?
In this project, we were one of the aims was to develop this methodology. So we gave them our methodology, and they can use it, of course. And since in March 2021, the European Commission ordered all European countries to monitor wastewater for COVID-19. The Czech Republic should also be included in this process and should monitor all cities over 150,000 people. But right now, we don't have any information on whether this monitoring ordered by the European Union is actually taking place in the Czech Republic. So we monitor wastewater only in our project right now, not for the government.
Yeah, thank you for the answer. As we observe the media, follow the reports in the media, there is no mention about using your method for the COVID pandemic management in the Czech Republic, which is a challenge for the future for your team in the institute. Yeah, I check whether there are another questions in the Slido. I do not see any questions, so we can continue with our presentations. Thank you very much, Lucia, for your complex presentation describing the method and presenting the prospects and potentials and challenges of this method. We hope we can follow your research in next future, and we hope to see the results of your research accepted by the political representation in the Czech Republic. I have now the pleasure to invite our next speaker, who is Mr. Josef Tregl, his colleague at my university. His presentation is focused on the innovative techniques for elimination of pharmaceuticals from wastewater. Josef, the floor is yours.
Thank you for introduction. I will share the screen, hopefully successfully. and I hope you can see, you can hear me, because I am always having problems with that. Can you see presentation?
Yes, I can see it. I hope the participants also.
Very good. So let me thanks again for the opportunity to present some of our results on this interesting conference. I would like to summarize a bit results we have obtained in the joint project Smart City, Smart Region, which we were invited to participate by Professor Jilková. Just briefly, our university is located in the northwest of Czechia, somewhere on the midway from Prague to Dresden, and bearing the name of Jan Evangelista Purkyně, who was born nearby. Nevertheless, I would like to continue with the pharmaceuticals in water. Pharmaceuticals are considered now among the so-called micro pollutants because they are present in low concentration in these wastewaters. Nevertheless, from definition, from the point of view of function of pharmaceuticals, they have high biological activity, and as all biological active compounds, they can have also toxicity. It just depends on dose what you get. If we account for pharmaceuticals in water, we have to also consider some metabolic products and degradation products, because of course, if we use the pharmaceuticals, our metabolic system changes them a bit. The wastewater is then containing also these metabolic products, and also on the typically on the wastewater treatment plants, there are many processes that change it a bit or a lot, but sometimes only a bit. So we have to focus on degradation products as well. If I get back to toxicity, we can find also special toxicity among the pharmaceuticals, which especially includes the endocrine disrupting activity. That means some of these compounds can affect operation of our, and not just our, but operation of the endocrine system. So it can disrupt with hormone regulation among humans, among the fish and other organisms living in the water. So this makes the base for the negative impacts on the environment. One of the problems, nevertheless, I can consider that smaller problem than not treating wastewater generally, is the fact that currently established wastewater treatment plants, which we use, don't work with these pollutants anyhow. Yeah. So of course the wastewater treatment plant eliminates part of these compounds, but it is estimated that only about 50%, which includes the biodegradation within the biological state of a standard wastewater treatment plant, or part of that is simply sorbed on the waste sludge. this is a bit problem as well, because the waste sludge have potential to serve, for example, as a fertilizer. Nevertheless, if there are too high concentration of these micropollutants, not just pharmaceuticals, this can then prevent the further use of this waste sludge. You may have heard that European Commission wants to ban the direct use of the waste sludge, exactly because there might be many of such micropollutants and they are not monitored. And they are not monitored especially because there are no legal limits for these micropollutants. So we have many indicators which are under legal limits, for example, nitrogen or chemical oxygen demand, which means sum of organic compounds, but we don't have any limits for these micropollutants. One option how to solve this is to include or enhance the so-called tertiary stage of the wastewater treatment. Standard wastewater treatment plants have at least primary and secondary stage. The primary is just mechanical, the secondary is biological, but some of the wastewater plants can have also the tertiary stage. They have it or they can have it, which means in fact the final purification of the already cleaned water before it is discharged into recipient, usually into a river. Some of our results, I will not tell much details because currently we are under the process of patent application. So I have to be very much aware what to present that could prevent some of the technologies to be patented. And nevertheless, here you can see the highest concentration of some of pharmaceuticals in the already treated, so-called, let's say, clean water before it is discharged to the Labe River. So it's from one of the wastewater treatment plants in our region. The concentrations are in nanograms per liter, which looks not much. And nevertheless, some of them are in hundreds or thousands of nanograms per liter. And I can say that we have also tested the input before the treatment. So then they are even higher on the inflow to the wastewater treatment plant. Nevertheless, this is what directly enters the Labe River and flows to Germany as a gift to our cross-border colleagues. You can find here many different interesting pharmaceuticals from different painkillers, inflammation or anti-inflammation drugs, psychopharmaceuticals, contraception. Positive thing on contraception is that it's not much soluble in water. Nevertheless, the more we can find then on the waste sludge. If I recalculate it in this case, this particular wastewater treatment plant produces about 300 cubic meters of clean water per hour. So, for example, in case of the carbamazepine, it's like 2 packages of the original drugs. In sequence to previous research, what we done here on our faculty, we are trying to focus, we focus on 4 different innovative approaches how to treat these micropollutants, which is sorption, then photooxidation or photocatalytic oxidation, and further biological degradation using immobilized microorganisms. I am having also one more lecture at the end, so I would like to speak there more about the potential of these techniques. So I will not go into much details now. I would like just to present you some of the results. First of all, I would start with my specialty, which is the biodegradation, the living system. So we did some screening on different microbes in the literature, how they are capable of treating of these various drugs. So you can find that not all microorganisms are capable of biodegradation. Nevertheless, some are, like the pseudomonads, bacteria. Nevertheless, we have found bacterium that is capable to degrade some of compounds. For example, here we have encapsulated a strain, a pure strain within organic material that very quite fast degrades the ethinyl estradiol, which is part of the contraception pills. You can compare to control that it really works, that it biodegrades. Sorption is very much popular generally. It's a method where you can combine various cheap or waste sorbents. So in this case, we were testing different biochars, partly in collaboration with the Bio company, a Czech small enterprise. And you can see that the performance of this material is very good. So usually in 60 minutes or maximally in 3 hours, we get below detection limits of these compounds. Photooxidation works even better. Here is an example of combination of the ultraviolet C light with hydrogen peroxide, which again results in quite fast degradation of these compounds from water. You can see that it's even faster than the sorption. The detectable limits after 60 minutes were only in a case of clarithromycin, which is antibiotics. We carry out some collaboration, especially with Czech companies, to try to transfer the technologies more to practice. One of the key points in this effort is the fact that there are no limits. So investment in enhancing the wastewater treatment makes currently not much economical sense. When limits might be potentially established, there will be significant pressure to invest in the tertiary treatment and to invest in the solutions. Nevertheless, we would be happy to find new partners, and especially for the upscale of the processes and testing of the real waters, not just from our region. Let me thank you for your attention, and see you later in the next in my next presentation.
Josef, thank you very much for your interesting presentation. We have now 10 minutes for Q&A session. I do not see any questions in the Slido framework or system. Maybe they will come later. I have two questions to you. Maybe some colleagues and some participants will join me. My first question is focused on the Germany. You have mentioned you have measured the content of pharmaceuticals in the Elbe River going to Germany. Are there any?
No, not in the Elbe River, in the effluent that goes to Elbe River.
Elbe River, okay.
The Elbe River distorts that a bit, yeah.
It goes then to Germany later. Are there any reactions or complaints from the German side regarding the content of this specific pharmaceutical elements in the water?
As far as I know, not in this case, yeah, because of course it's not just Czech problem, it's the same as Germany has got the same problems. We were once preparing the cross-border project with German, with TU Dresden and few other partners in Germany to monitor more these pharmaceuticals as well, and also drugs, yeah, especially like pervitin, heroin, and these compounds. So we are trying to get funding for this wider monitoring. Nevertheless, you know that the Elbe River used to be a very polluted river before the Velvet Revolution here. There are like 10 different chemical plants on it, and not majority of them did not have any wastewater treatment before 1990. Now it became much better. So the Germans now, I think, don't have much to complain on, because even the Elbe River is regenerating a lot. Yeah. Between Ústí and Dresden, where the river is more nature-like and not as regulated as the remainder of the river. You can even find now the protected species of some animals that appeared there 20 years after the wastewater treatment was established. Yeah. So no, I don't know about any complaints, because from global point of view, in last 30 years, it became really 1000% better.
Yeah, this is nice to hear. Thank you very much for this optimistic answer, positive answer. I'm looking for questions. I do not see any reactions from the participants, and so we might go to my second questions. You have mentioned more times there are no legal limits for the pharmaceuticals in the Czech Republic, and therefore it means there are no regulatory incentives to invest in new technologies and to develop new models of wastewater treatment. Could you compare, I hope you have the knowledge about other countries and in the EU, could you compare our legal framework with other countries in the world? Are there countries in the world they have limits for these specific pharmaceuticals? And the second part of my sub-question is, how is the political representation doing in this field? Do they prepare any regulation for these pharmaceuticals? What's the prospect of this legal framework?
I must frankly admit that I am the limits and the regulation is not especially my business. We more focus on the technologies. Nevertheless, as far as I know, in EU that there are no such limits. Nevertheless, in the Water Directive, there are some aims to establish them in future. Yeah. So that's what. But I am really not very skilled in legislative and regulation. So it may change, or maybe in the north countries which are always like in a bit ahead of us in the environmental protection, there might be some limits, but I don't know. Sorry.
Yeah, this might be an issue for next dissertation at our university to examine this issue more in detail. Thank you very much. I do not see any reactions from the colleagues from Nordic countries. This would be very interesting, but I fully understand this is a specific topic, this regulatory environment. We will check it later, how is the state in the Nordic countries. We do have some minutes time still. I might ask Mr. Kappanen whether he is prepared to deliver his presentation, so we might start some minutes earlier than planned. Is it okay?
That is perfect, and do you hear?
Thank you very much for your reaction. So I kindly invite you to present your presentation, which is called Wastewater Recycling. So with your presentation, we come to the second part of our event, which is focused on the recycling. After the state-of-the-art analysis, then we will now focus on the recycling. Jaakko, it's your floor.
Thank you, Irina Jirkova, and Debrecen. Hello to all. Yes, and thank you for this opportunity to squeeze my 40 years experience in 20 minutes. Let's see how I can do it. And the wastewater recycling background for this knowledge is I'm metallurgic, Master of Science, and I've done like licentiate thesis on glycols. And by that time I learned the chemicals, how they do pollute waters. While working on the steel manufacturers, big companies, and plating companies, for example, and chemical companies, I got involved in this water issue. And of course, money is running the companies, and that was one issue early 80s already, that water should be reused. More after a couple 20 years after that, people start to talk about recycling. So that is to start my presentation. Few facts about water in Europe. The average available renewable freshwater resources per capita among European countries is highly variable, ranging from less than 100 cubic meters per person per year. In Malta to about 500,000 cubic meters per person per year in Iceland. So there is a lot of differences in that. A relatively low available renewable freshwater resources is measured in half of European countries. In the past years, the topic of water scarcity and drought has moved to the top of European agenda. In EU report, Water Scarcity and Drought stated that water stress affects 100 million inhabitants, 30% of the population in Europe. Not only the Southern Europe, but also in northern countries such as Belgium, Denmark, Germany, Hungary, and after Brexit, still I have here the country United Kingdom. Just to mention here about the Germany, I learned water recycling and wastewater treatment at Duisburg in the steel manufacturing company, and they took the water from the river, and it was much cleaner than we let it out back to the river from the steel factory site. It was very interesting time to learn how Germans did it. Today, in the EU level, there are several efforts that are focused to save our water resources. So now it comes up to the state level. We have Industrial Emission Directive and I have been working with the ECHA, European Chemical Agency, with these directive issues. 21 PREF documents, among other legislation, to reduce pollutants. Now in Finland, we have started to collect for plating industry the group of experts to do the next PREF document. So that is just as we started to collect people on September, and I'm one of the volunteers, let's say. There are the chemical bottles. Meaning of those is that while I was in the German chemical company called Henkel, I learned, as being a part of the core team for several years, the raw materials that are used in households, in industrial chemicals. And again, I faced the problems that how wastewater plants can treat all those various raw materials. How can they clean it? Not only nitrogen or phosphate we are talking about. We are talking about very, very small amounts of hydrotrophs, tensides, complexing agents, which are really important to know when doing recycling. The water services as the framework of circular economy is quite large. There in a red area is today's topic. There are municipal community factors, water treatment after water field, drinking water distribution, wastewater treatment, after that sludge treatment, nutrient recovery and recycling. And to the Mr. who had the presentation just before me, he was asking about the regulation. So in Finland, we have hot topic on these sludge treatment regulations. So that is different regulations in each EU country, let's say. I'm not a expert on that, but I've been sitting on around the tables that they have the tight restrictions to the sludge. From circular economy, we are going to reuse water or not. It depends on the cases. Intake or recycled water quality. I start from the quality issue. Freshwater quality influences strongly when selecting the wastewater process, as well recycling possibilities. In Finland, we have the highest top quality fresh water, was stated by the United Nations. I think it was 5 or 4 years ago. I've been working in Norway, and in Norway, the fresh water from the rivers, from the mountains, that is as like demineralized water or distilled water. It is very hard to work in industrial level or in tubing, because there is no calcium, magnesium ions that makes a protective layer to the tubings. Just to mention the high mountains that they collect the waters there, and pumping problems. While in some cases, softened riverbank filtered water can be used. That's still in Finland in several cases. Generally, it's known that high total hardness is common in EU or too high boron, as in parts in Italy. I faced that problem a couple of years ago in the few companies I was consulting. I don't know the situation in Czech, but I think you have this high hardness as well over there. After the wastewater, of course, and the chlorides corrodes iron and steel materials as organics harm filters. And one fact is that before Finland joined European Union, there was a chloride limit in our drinking water, 100 milligrams per liter. That was pretty good level, because in the European Union, it jumped up to 300 milligrams per liter. And guess what? 300 milligrams chlorides that corrodes quite heavily the wastewater plant tubings and other goods in our water maintenance system. While after the wastewater treatment plant, some impurities are still left in the water that would be or want to be reused, recycled. Quality must be carefully characterized, including exact limits. When using recycled water only partly to the system, user needs to know the cyclode concentration to avoid too high amounts of harmful components. Diagnostic tools, sensors, and software applications are nowadays used to manage concentration to appropriate levels. But plus, we should not forget the traditional laboratory work in these analyses. As in the previous presentation, the chemical wastewater treatment lines, those are what we are facing in Europe, and in recirculation purposes, the traditional direct precipitation is not enough. It makes more difficult this issue of wastewater treatment, because when we have a direct precipitation, that is typically the time that takes to clean the water is 3.5 hours. Then we add their precipitation and pretreatments. It triples the time. Different precipitation, pre-precipitation stages. When they are effect processes, that is 8.5 hours. If we have post-precipitation or tertiary processes after the normal chemical wastewater section, here we go up to the 13 hours. So it is a time issue as well. So the wastewater treatment lines needs more processes units to purify wastewater down to accepted level. And I have followed during my career time that in the 80s it was very, very simple, these wastewater treatments. Today we have these tertiary treatments that is more or less, we find it all over today. And as we go to next slide, I want to focus on few requirements to control recycling. Regular analyses, metering unit checks, plant inspections, corrosion measurements, information of responsible personnel, and feedback from all the information collected from the wastewater plant is very important. Today we use monitoring software, proper software, automatic control for water data, and good maintenance of probes helps us to do that work. Interpretation of the treatment results, we need consults maybe outside from the wastewater plant. Typically in Finland, the size of the city inhabitants, let's say 25 to 40,000 people, they have a wastewater treatment plant which has less than 10 people working in there. So they need consultants and other experts to run the plant. There is so much today to be known exact, let's say, that is not science, but how to run the lines. The laboratory studies and interpretation analysis of solids, surface analysis, etc. What do they tell to the workers how the process is running? Frequent monitoring and reporting to official is often required. And each wastewater plant has their own limits that they can they have to obey. Also, I have faced many times this microbiological growth. It makes always costs. And the important role of biocides. I picked up a few biocides here, and in my experience, sooner or later the biocides are needed. We have to follow the local regulations and use accepted chemicals when needed. You know much better this biocide issue as micropollutants, but here are a few facts that historically against fungi in plant operation, Dazomet was the first with clausal will not pose unreasonable risks or adverse effects to humans or the environment. And also there is the other THPS chemical, and from the year 1995, Environmental Protection Agency of the US ranked this with zero toxic chemical and was awarded with US Global Green Chemical Prize. Well, let's go back to the 80s. We pumped into the wastewaters huge amounts of polluting chemicals. And in next slides, I want to go to point out that these chemical treatments, officials have tackled it by piece, and in drinking water treatment, we have certifications. They are coming from the United States. This is one of the, I want to point out, this NSF 60, drinking water treatment chemicals. This standard contains health effect requirements for drinking water treatment chemicals that are directly added to the water and are intended to be present in the finished water. This issue came up when I was in the project that in Singapore, they are using cleaned wastewater. They are recycling wastewater into the drinking water. 30% of the drinking water in Singapore is produced from the wastewater. That was quite surprising 10 years ago when I was in that project. And this NSF standard was very important, kind of a level that we had to stick in. That standard connections covers even to drinking water plant constructions in more details as materials, coatings, etc. at site. So the standards are globally and accepted the public health standards. Then recycled water is aimed at tap water regulation that should be followed carefully, and here is the link to organization sites. This latest version of this NSF 60 standard will be in effect 1st January 2022. And here are listed few typical chemicals that are needed in drinking water treatments, and they are coagulants, flocculants, disinfection and oxidation chemicals, pH adjustment, softening, precipitation, specialty chemicals. While I was working in the chemical industries, raw materials, there are available a lot of these water treatment chemicals, and should be taken very good care that where the wastewater plants they buy those, there are impurities. There might be impurities in the products, and when you are aiming to recycle the water, you have to think carefully that what is the target for on recycling the water. Does it go to drinking water? Does it go only to inside the industry? So take care that you buy the right quality water treatment chemicals. Advanced wastewater management to reuse water. There are few things I would like to highlight here. Those impurities could be coming from the intake water that disturbs normal cleaning process critically, or they comes from the wastewater. Is it from municipal side? Is it from industry side? Doesn't matter, but there comes disturbing units, that's for sure. In industry, it is easier to remove the source of pollution or isolate the disturbing unit. In in-house recycle cases, that removal of undesired components before entering into the main process, that is good management. And use a correct policy instrument, follow the environmental permits. That helps to keep the process running on the right quality level. Quality targets, cycle of concentration, and everyone who is doing on water treatment business, they know the cooling tower's basic technology, that when the feed water is added partly to the system, the concentration of the harmful ions, they typically go higher and higher. Then managing the technology, targeted technologies, we have to think the source of separating systems. There are a lot of technical processes to select from. One is to control on a pre-treatment level, wastewater treatment plants, using enzymes, de-emulgators, filtrations, and dozens more technologies are available. For example, there are oils, different oils coming into the wastewater plants. Those stuck the filtration, mechanical filtration stage. So one pre-treatment, and here could be the emulgator that breaks down the oil films. And frequent environmental impact assessment should be done. There is all legislations focused, which are collected the information to the environmental permits, and we have to inform the officials, not every year, but quite typically in 4 or 5 years, and rename the levels of the impurities and pollutants. And of course, when improving the processes, the cost and risk assessment should be followed by proper plant maintenance. Nutrient recycling is today a very hot topic, and risk that should be followed, risk management in sludge treatments. And there are several projects running in Finland of different sludge treatments. Are those done at site, or should be the sludge treatment collected in 2 or 3 places around Finland? So very interesting issues. Now we go to advanced wastewater technologies to reuse water. When I was starting this recycling of water, that was quite easy. The pollutant levels were quite high, accepted, and some pollutants were just allowed to put on the wastewater. Today, the strict legislation makes it that is a must to do, for example, tertiary treatment at wastewater plant. Chemical treatments, not only the classic ones, but new chemicals processes are available. Oxidation with all its different oxidation forms, not only the wet oxidation, but then we go, for example, case Sansox. There is a tubing that is water and gases are mixed very, very well together, and it oxidizes the impurities, for example, that is used in the caviar farm plant in Finland. And that makes the water possible to recycle. Ozone could be used with combinations also in pretreatment. UV light, different wavelengths. I have been with in the projects where we studied different wavelengths, and it gave very surprisingly different results in the cleaning wastewater. And ultrasound, we should not forget that. New steps have been taken in sorbents, granular active carbon, zeolite, silica-based compounds. Those are the classical ones, but there are now different new approaches on the materials. Filtrations are in tertiary step, nanofiltrations and reverse osmosis. Those are definitely has to be used when doing drinking water quality. And the next slide has later I comes to this pulsed corona discharge, which is new technology in our markets. And the technologies are really taking good steps on sludge management. And there are projects, as I have been telling, is on the nutrient recovery, and also an interesting issue is hazardous waste separations and treatment technologies. And there a case is that on the markets we have a direct heavy metal precipitation with a sweeping method over pH. It takes 100 times more effective heavy metals to precipitate than the hydroxide precipitation method. That is used in big water uses like in mining industry, but could be used as well in recycling in municipal site as well. Few technical solutions to pre or tertiary stages in the 2020s is there. I told about the novel fiber materials and solutions for extraction of metals, radioactive and
organic. I'm very sorry, as a moderator, I have to remind you about time.
Okay.
We have 5 minutes, so like 5 minutes time, please.
Thank you. Thank you. So there's a selective membranes. We have in recycling tap plating line that removes nickel ions and they recycle water. Electrocoagulation, that is patented chemical path configuration. There's a pulse charge discharge, and here is that flow chart, how we take disinfection medicine residues away and special harm for wastewater streams. Now, we hear today more about these drugs on tap and the innovative approaches. There are all the time going on, but first slide here is I want to introduce the Finnish Water Forum. That is a platform over 130 members that includes research and educational institute, associations, companies, and 5 ministries. We are a non-profit organization, and our mission is to find solutions to global water and climate challenges through Finnish know-how and technology together with local and international actors. We are offering partners in the field of wastewater recycling technologies and management issues on national, international levels. We are offering knowledge partners to find solutions to water-related challenges at site. And we provide project expertise through Finnish know-how and technology together with local and international actors. So we are one-stop shop to water-related challenges. And when you are looking at a partner, you can contact me so I can start discussing who could be the partner for you. Thank you for your attendances. And
Jaakko, thank you very much for your presentation. You have presented a very detailed picture about technologies and the advances. But you have mentioned more times the requirements to control recycling. And you are project manager for the Finnish Water Forum, which is really a large network of institutions.
Yes.
Could you give us the information, what is in your view, in your perspective, the main gap in the regulatory environment? What's missing in terms of requirements and regulatory pressure to incentivize more recycling, more water recycling? What would help?
Well, in Finland, we have enough water. Yes, that is an issue. When I have been traveling abroad, there's a scarcity. That is, let's say, I'm not an expert to answer to that question. I've been traveling in Africa. I've been traveling in Russia. I know the quality of water they are drinking there, and that is awful. But I don't have the answer to your question. I'm sorry.
Yeah, maybe the answer to what might incentivize it's the water scarcity as to your experience, not the legislative framework, but just the water scarcity. When it comes, then the incentives come.
I was working in a chemical company Finnish chemical company called Kemira, and I was running over 10 million euro project with 36 doctors in my team. I was surrounded by the experts, and we were working on desalination plants where they are making good, fresh drinking water. And then there came the Arab Spring, the war in this area, and none of the desalination plant was demolished. No rockets was shooting to the drinking plants, desalination plants. So those guys did know that this is something so important issue, the water, that we don't shoot those down.
Destroy the infrastructure.
Destroy.
Yeah. Thank you very much for your presentation.
You are welcome.
And thank you. I have now the pleasure to invite Professor Jan Bartáček from the University of Chemistry and Technology in Prague. And he's going to present about the developments and constraints in greywater reuse in Czechia. Professor Bartáček, Jan, the floor is yours.
Thank you for introduction. I will share my screen now. Now you should be able to see my presentation. Is that the case?
Yes, we can see.
Maybe one question. Do you see also the mouse, the cursor?
Yes.
Okay,
yes,
perfect.
we can follow the.
Okay, so my presentation today is on the greywater reuse in Czechia, really focused on Czechia. As I was asked to give this presentation, to introduce myself, I'm from the Department of Water Technology and Environmental Engineering from the University of Chemistry and Technology Prague, and I'm the head of the group of anaerobic biotechnology. What we do in the group is mainly resource recovery from wastewater. We look at water reuse, their greywater reuse mainly, but also energy recovery, materials recovery, and information recovery. Actually, that's something that is part of that is taking most of my time nowadays, because we quite intensely follow coronavirus in wastewater in Prague, and actually as the authorities started to cooperate with us, we are rather busy with that topic. But indeed, greywater reuse is still a very important topic for us. Why we focus on that so much is that if you look at the total picture in the Czech Republic, if you look at the withdrawals of water sources, then this is the history from 1990s to more or less the current situation, when all the consumption went lower by the factor of 2 almost since the 90s. But still, the main consumption of water is in electricity supply. But then the second main consumption is actually public water supply. If you look, for instance, at the agriculture, we use only 4%, at least officially withdrawn water for agriculture. Only fraction of that is irrigation. So if you want to do some important action in water savings, indeed you start with the larger parts of the cakes. And then as if we look still more closely to the public water supply, then you see that over 50% is consumed by households. About 25% are other users in the Czech Republic, indeed. And then, yeah, I see there is some problem with visualization in my picture, but anyhow, I will comment on the different shares in the water use in households. So far, the largest is the use in baths, in showers and bathtubs and so on. And then also large amount is used for washing the clothes, so washing machines. Very minor parts are used for cooking and drinking and so on. And then about 23%, I'm sorry for the visualization here, but only 23% on average, these are Prague data, is used for flushing toilets. So if you recalculate this part of flushing toilets, 1/4 of household use, to the total withdrawals, it's about 5% of the total withdrawal in the Czech Republic. So it's even far more than what is used for irrigation in Czech. So if you want to reuse some water, then the best is to use for, at least to start, is best to start with flushing, because then you can save more than what you save, for instance, in irrigation. It's a very low-hanging fruit, because you don't need to look that much at the quality of the flushing water, at least in terms of discharge limits or something like that. So what is gray water? I think most of the people know nowadays. So that's exactly the water which is produced in bathtubs and sometimes washing machines. And where that water can use, I'm really sorry for the visualization here, but it's mainly for flushing toilets in the household and washing machines. Other uses, like for showering and so on, it's problematic indeed. Also, it is possible to use it, for instance, for watering the plants and so on. But then what is interesting and what is nice, that the production of gray water always match with the possible use of treated or reused water or treated water in the households. In the households, we have always more gray water available than what we can normally use for flushing and washing clothes. But it's always a sort of close balance. So why we look at the gray water use? First of all, it's large portion of the total water use in Czech, and then it can be easily used in the point of production without any transport, and it's really a large portion, at least potentially. So at the moment in Czechia, we have some systems in family houses applied. There is no official list of these systems, or we don't know exactly how many are applied already, but we know that about 60 projects have been supported by EU funds in the program which is called Discharge, which means basically rainwater. It's mainly focused on rainwater use, but also grey water systems are supported there. Then the problem, and I will talk about it much more, outdoor use of grey water is illegal. in any case. So you can, even if you treat your grey water in your family house, you cannot use it for irrigation of your garden, for instance. At least legally, you cannot do that. Then we know there are several large systems installed in apartment buildings. I will also comment on those. There are also some in hotels and administrative buildings. Unfortunately, there is no system evidence or how do you call it, control from the state authority. So we don't really know how many and where all these systems are. We know here and there, but we don't know exactly the total picture right now. Now, my presentation will be mainly based on a study that we were invited to do for the Czech Ministry of the Environment last year. And they basically asked us to do the study which would review the situation worldwide, that would review the situation in the Czech Republic from the point of view of technical solutions and legislation, and to suggest the steps that Czech Republic should take to support this field. And they also ask for parameters for the systems that they should support by governmental or EU-funded funds. Now, indeed the study is in Czech, so I can only recommend it to Czech colleagues, not to our international colleagues. But basically, the content was a review of the state worldwide, review of the field in the Czech Republic, the definition of required actions, description of typical solutions that can be applied, basic requirements for governmental support, and also water saving potential for the whole Czech Republic. So we call it absorption capacity. I will quickly go through the reviews. We reviewed over 30 relevant standards worldwide, legal or technical, all around the board. I cannot go into detail. It's a really large amount of information which is collected there, but in principle, indeed, the standards are very variable. What is, however, the common emphasis for all of those that are well done is the emphasis on the risk assessment, concrete risk assessment for the concrete situation, so the object where grey water is produced, and also where the consumption, the type of use of the treated water. So this is something that is already incorporated in Czech legislation, for instance, for drinking water supply, and we strongly suggest that this should be part of legislation also for the for grey water reuse. And for the technical solutions, of course, there are a huge number of technical solutions. In principle, you can find whatever techniques related to wastewater or water treatment. In principle, we can end up with distilled water if we want. So, of course, there are technical solutions available, but there are also technical solutions which are affordable for grey water reuse. And we clearly demonstrated that almost any type of buildings, from family houses to airports, for instance, can be equipped with grey water reuse. Indeed, the water produced can be of a good quality if you design the system well and if you operate it well, actually. What is a problem in view of, for instance, technologists or investors in the Czech Republic, that the data on, for instance, water use, water consumption are very different worldwide, and we don't really have a good basis on the information basis where we would found the information of typical consumption in, for instance, administration buildings or office buildings or commercial centers in the Czech Republic or in hotels. So this is information that still should be better collected in the Czech Republic for the investors to be able to design, or not only investors, also suppliers, of course, to design sufficient volumes, for instance, and sufficient technologies for these atypical buildings. As for the Czech Republic, we reviewed strategic documents, so to see whether the government actually wants to support the field in the Czech Republic. Indeed, there is a declarative but strong support to water reuse in general, and specifically to grey water. But the problem is that this is not really mirrored in real legislation, in real acts and water standards and so on. I will talk about it still more in detail later. Then as for technical standards, we can use all sorts of standards from all around the world, and there are very good ones. In Czech, we have now adopted the EU standard on-site non-potable water systems and Part 2 systems for the use of treated grey water. So technically, there is no problem to design nowadays good systems, well operating systems, and people or the suppliers also are able already. We have cases of good practice here in the Czech Republic, so this is definitely possible nowadays. The main problem, I would say, in the Czech Republic is the legislation in this respect. In the study that I presented, we went really into detail in this field. So you have to look there, but here I just stress the most important ones. So first of all, there is this Act number 254, which is, I don't know the correct English translation, but it's water protection related law, basically. And as for water reuse, there is declarative support to water reuse, but nothing really practical. And actually, it is very hard to somehow get compliant with this specific law if you want to reuse wastewater. Most importantly, I would say it is technically impossible to use reused wastewater, for instance, for irrigation. There are a number of reasons. First of all, irrigation is seen by Czech authorities as a discharge to groundwater body, which is one of the only 3 possibilities what you can do actually with wastewater nowadays in Czech. You can either discharge it to surface water or to groundwater, or to transport it to wastewater treatment plant. Simply said, let's say. So if you see irrigation as dumping to groundwater, you can only do it when other possibilities are not technically possible. And you can only do it if you have up to 15 cubic meters per day, which is most often okay for grey water use, but you may have some buildings where this is not enough. And also, if you want to irrigate, you would probably want to kind of protect public health, because there will be aerosols produced with pathogens possibly. But if you, this is absolutely not foreseen by the law for groundwater discharging or wastewater discharge to groundwater. So there is nothing about Legionella, for instance, or other pathogens which may occur in wastewater. So this is a big problem from our point of view. Then there is a public health protection law, which actually from the coming February will effectively introduce the terms of grey water reuse and processed water and so on. But the problem is that there is clear contradiction to the water protective law, which I introduced a slide before. So there is a very strong inconsistency in different laws. that should concern somehow greywater reuse. So this is a problem that needs to be seen and needs to be repaired, I would say. Then other problems is that there is no standard procedure for public authorities when new systems for greywater reuse are judged or introduced into public. I mean, if you build a building, whatever apartment building or so on, and you want to have a greywater reuse system there, it will you don't know what are the limits for the produced water. You don't know what are your duties towards public authorities and so on. That's a big problem indeed. And there is also no control whatsoever on the systems built in older buildings. So if you have an apartment building now in Czech, which is already built and people live there, and you introduce greywater reuse system, public authorities don't care at all. So we've seen many or quite some systems in these buildings which are absolutely not working well and are actually maybe danger to public health, to people who live in those buildings. And as I said, a big problem is that irrigation is effectively not possible at this moment with treated water. Now, for technical solutions, we have a number of good examples. I think the Mercedes among them is the case of Botanica, which is a building built by Skanska, so Swedish company, who did very good job in adapting very good technology. You see it here in the picture. It's a very stable, actually German technology, which is there, which is well operated. I will talk about that a little bit later, a little bit later. This is all based on membrane bioreactors, which is the most frequent case. But you can have also less advanced technology. This is actually in my house, to be honest, which is based just on biofilter, which again, if it's operated well and which is if it's designed well, gives perfectly good results comparable with MBRs.
Professor Bartáček, I'm very sorry to remind you about the time.
Okay, how many minutes do I have?
Yeah, we are a little out of time. You have 2 minutes, please.
Okay, then I will have to skip some pictures. I wanted to show some data from these systems, but we can skip it for now. Probably the PowerPoint will be available. I just wanted to stress that, for instance, in these buildings, the quality of water which is produced there is almost drinking water quality. So yeah, you really can have a good, well-operating systems. The most frequent problems there are insufficient capacities designed, improper combination with rainwater, which, as I said, you always have enough greywater if you want to reuse it in a household. No sense to combine with rainwater collection system. But if people do, often the quality of water deteriorate. Insufficient disinfection, often not sufficiently operated or sometimes even switched off, and sometimes not sufficient separation from drinking water distribution systems. So the most urgent actions that we suggested is the modification of Water Protection Act to allow irrigation, for formulation of standard procedures for public health authorities while evaluating new greywater or old greywater reuse systems, definition of requirements for treated greywater, guidelines for risk assessment, and collection of relevant data on water reuse. Now, this I will skip. Then we also look at the potential of water reuse in the Czech Republic. We had 3 different scenarios, which was one conservative, realistic, and optimistic. Optimistic means that all greywater is reused. Conservative if water is reused only for flushing. And then we calculated for these scenarios how much water can be, for instance, saved in hotels, on all sorts of buildings, and also for the whole Czech Republic. So we only in households we can save this way something between 60 and 180 million cubic meters per year. Okay, I will switch this, and the conclusions, I'm sorry for the Czech word here, the main obstacle is inconsistent or missing legislation. We have to define legally grey water, we have to define standards for public authorities, and we have to allow grey water irrigation. And the technical solutions of high quality and reliabilities are of course available, just have to be applied. So thank you for your attention, and I'm sorry if I was a little long.
Professor Bartáček, thank you very much for the presentation. It was for me especially very interesting because I'm dealing with the legislation, regulation. I do not see any questions in the Slido. My general comment, I got the impression that Czech Republic is quite restrictive in the legislation. I would call it even not fit for purpose in terms of grey water use.
Yeah, there is, I think, yeah, how to say that? I think there is no there has been no legislation, still not in effect, legislation on grey water reuse. But still in family houses, people were able to apply it, in apartment houses also. The problem is, especially for the investors, that you don't know what to prepare for, you don't know how to design your system to comply with the legislation. We are trying to change that, and there are some initiatives working on that, but still some time is needed.
Yeah, thank you very much. And I really appreciate your complex knowledge about the regulatory environment. I do not see any questions from the floor and from the Slido, so I might now invite again Dr. Josef Trägl to present about the water purification using photocatalysis, electrocoagulation, cheap sorbents, and encapsulated bacteria. Very specific presentation about technological process. The floor is yours.
Thanks again. Let me share the screen. Can you see the presentations?
Yes. I see the first slide.
Yeah. So in fact, we discussed that you are lacking one more member. So on this conference, so I propose to summarize a bit our previous research and possibilities, which in fact we currently continue on with the pharmaceuticals. So I will go through it a little bit more quickly with some examples of previous published results.
Yeah, thank you very much. We are a little bit running out of time. Then, if you could.
Yeah, I will go on quickly.
Little bit.
So, as Faculty of Environment, we focus a bit on water as well, of course, including the wastewater treatment technologies. But I would like to speak about a little bit of non-conventional sorbents, photocatalytic oxidation, and biological treatment and electrocoagulation. I will start with the non-conventional sorbents. This is a long history research here on our faculty around Professor János, who also proposed me the work on our faculty 15 years ago. What they were initially researching sorption of different pollutants on many waste materials such as fly ash, spent sawdust, or modified materials. Also modified nature materials such as metallic humates from cheap coal, or more recently graphene composites which have high sorption surface. And the most recent research is on let's say artificial sorbents based dominantly on metallic oxide, and especially on cerium oxide. Professor Janos loves this part of periodic table, the lanthanoids, so he likes to work with cerium oxide, and it has got a lot of interesting properties. And also quite recent research has been focused also on practical modifications such as preparation of magnetically separable sorbents which have the reactive part and magnetic core, or hydrophobic sorbents and things like that. Really the latest specialty of this team are the reactive sorbents. So it's not just sorption of the material, but the sorbents provide some form of catalytic properties. It's not always pure catalysis, yeah? But generally yes. And especially the cerium oxide can provide catalytic properties on organophosphate compounds. These are quite toxic. You may know them either as pesticides, such as parathion-methyl, or also the chemical warfare agents such as soman, sarin, tabun, and these highly toxic compounds. So these cerium oxides are capable of decomposing of these organophosphate materials, which you can see here on this sample chart. You can see that the elimination is quite fast, and we get to almost 100% conversions after like 2 hours. Here you have some examples with the real nerve agent, soman and VX. This research was carried out with the help of the Military Research Institute. We really don't work with soman here in the laboratories where students have access. That would probably lead to an undesired loss of students. What is also interesting that these materials can interact with, let's say, standard biochemical compounds such as adenosine triphosphate, DNA, etc. Nevertheless, it has not much to do with wastewater treatment, so I just leave it here as a sample. Photocatalysis was introduced about like 10 years ago. I mean, here in our faculty. Otherwise, it's quite a known process. Even currently, there are marketed products such as the titanium oxide-based paintings on wall, which provide also the photocatalytic activity, so that the painting does not get as much dirty during time. It has self-cleaning properties. Nevertheless, what we focused dominantly on here was the homogeneous catalysis. I'll try to use some form of pointer, and homogeneous catalysis, homogeneous photocatalysis is not as much established. The most positive thing on this is that a lot of homogeneous photocatalysis work in standard visible light. They, unlike the titanium dioxide, which requires generally the ultraviolet light, more energy and less safe, these homogeneous photocatalysis can work under visible irradiation. Our research went like into two main directions. One was on using microreactors, which enable study of the exact mechanism of the decomposition. On the other hand, we collaborate a lot with the industry, so we have also the semi-pilot scale, or maybe quarter pilot scale reactor that can be used for the real water, real polluted water purification. Here you can see our so-called photo bench with the photoreactor, where you can really precisely set all the properties starting from the wavelength of the light, the different filters, intensity, temperature, oxygen, no oxygen, all you need here. And just few examples of results. Dominantly, the research was carried out with these phthalocyanins, which are tetrapyrrole-derived compounds. They are by structure similar to many, like say, nature-based compounds such as chlorophyll or hem as a part of hemoglobin, our blood dye, and so these compounds can be found in nature. Nevertheless, these phthalocyanins are modifications, so they are not nature-based, and they have very much interesting properties. Especially they are non-toxic and they are quite cheap. Some of them are even used as a textile dyes, for example, for the blue jeans. This is very popular. So here you can see some sample of results. So this is hydrogen peroxide UVC elimination of chlorophenol using also these phthalocyanins as a photocatalytic photocatalysts. Here you can see the dye, how it looks like, the molecular model, and you can see that it really works quite well and again quite fast. Chlorophenols were provided, or the chlorophenol polluted water was provided by the Deconta company as the real wastewater from their one of their processes. And now a little more about my scope of...
I am very sorry. 2 minutes?
Okay. Immobilization of microorganisms leads to many positive effects. Nevertheless, it also leads to some more costs. We are like nature inspired because microorganisms in nature tend to immobilize themselves, for example, to biofilms, and probably the most positive on the artificial immobilization is the protection, so that the immobilized microorganisms then can work in an environment that is somehow more hostile for them, such as toxic or highly saline. So in this case, I will show you just our results, which we carried out together with the Lenticats company. However, this one does no longer exist. It was sold, but the technology exists. And it was focused on the wastewaters from the sulfuration plants from the coal power station. So we had water which was lacking almost phosphorus, was very highly saline, and lot of nitrates and nitrates, lot of COD organics, but not much degradable. So here you can see that we have successfully established long-term continuous experiments that provided quite high denitrification activity and could be used for this form of treatments. And as final electrocoagulation, it was mentioned here by one of the speakers as well that it's applied. So electrocoagulation, in fact, is a form of substitute to standard coagulation methods that are often used in water purification system. The positive thing is that generally you don't need as much chemicals to put into the water because they are partly substituted by the electrochemical reaction, which you can see here on the comparison. Here is our semi-pilot scale or quarter pilot scale reactor for electrocoagulation. We have tested different applications, and as one example, these were again the real wastewaters with lot of different toxic metals that were successfully treated this way. Again, I think in collaboration with the Deconta company, which is one of the biggest companies focusing on decontamination. Again, we would be happy to try new real applications with new partners. And thank you for attention.
Josef, thank you very much for your presentation. As I do not see any questions in the Slido, I would leave the potential questions for the bilateral communication via email or telephone calls. Thank you very much for your technical knowledge. We have now the chance to approach to open the last presentation, which will be then delivered by Jacek Kościukiewicz from Cambi organization. One
moment.
He's here. His presentation is about municipal sludge as a product in circular economy.
Yeah, so let me just share my screen with you. Okay, I hope I shared my proper screen with the presentation.
Jacek, I still cannot see your presentation. Maybe the other participants may, but this is not my case.
One moment. Yeah, it should be right now, I hope.
No, not. Oh, yeah, okay.
Okay.
I see. Thank you.
Yeah, I have two displays, so that was, I wasn't sure which one was shared. I would like to say a few words about the how we can consider the municipal sludge which is produced in the wastewater treatment plant in the age of the circular economy. So I would say that my story begins very long ago There were just a few people on the Earth, and our planet was able to recover from all injuries which we caused. The more we were possessing the Earth, the more difficult its recovery was taking, until we have reached the point of no return. So this means that we should do something, otherwise our successors will not have the place to live. And to do that, the international community decided to change it, to change the way how we use the Earth and its resources. And the circular economy is just one of the many ways which we want to use to make sure that we will leave our planet for our successors. The definition of the circular economy developed in the European Parliament states the following. The circular economy is a model of production and consumption which involves sharing, leasing, reusing, repairing, refurbishing, and recycling existing materials and products as long as possible. So there was developed the framework model by the authors, Small et al. And I will mention the source later. And this framework model says that the model is developed particularly for the water and wastewater treatment sector. And the model assumes the 6 R's. And the first R is the reduction. It is the prevention of the wastewater generation by reduction of water usage and pollution at source. That was already mentioned before. The next is the reclamation, which is the application of effective technologies for the removal of pollutants from water and wastewater. The following is the reuse. We can reuse the wastewater as an alternative source of water supply for the non-potable usage. And it was also mentioned before. We have also the next R, which is recycling, the recovery of water from wastewater for potable use. It's also mentioned before. Recovery of resources, such nutrients and energy from water-based waste. And finally, the last but not least, it's also very important, rethinking how to use the resources to create a sustainable economy, which is free of waste and emissions. This is the source, if someone would be interested in the details of this framework model. There are several things we may recover from our waste water. Let's just mention a few of them. That's the most common, nitrogen and phosphorus, but also the other, like the cellulose, the humic acids, fatty acids, enzymes, or polysaccharides. Some technologies already exist and are quite commonly used, and some still require improvement because they are present in the prototype state. The Biocore recovery technology exists also, but it is at the present time used in rather small plants. What I would like to focus on are the biofertilizer, electricity, and heat. The anaerobic digestion of municipal sludge is widely known and commonly used, so I will not go into details. The both primary and waste-activated sludge are mixed and sent to the digestion chamber. Then produced is biogas, which is burned into cogeneration and what produce the electricity and heat. As we see, the conventional anaerobic digestion process give us three precious products: electricity, heat, and final sludge. This is the place where the final sludge is produced. In general, there are two groups of final sludge disposal. The first one is the thermal applications, and the second is the land application. At present time today, I will not discuss the thermal applications because it's only match partially the concept of the circular economy. I will rather focus on land applications. The Sludge Directive regulates conditions of using the sludge in agriculture. Among the other things, it describes conditions of the application, reporting obligations, and from the important thing from the processing point of view, the limits related to heavy metals. However, of course, we shall remember that heavy metal content in the biosolids is the consequence of their content in the raw sludge and the quality of the wastewater treatment. The anaerobic digestion does not change metal content, but it increases its concentration due to the reducing of the sludge amount. Then we have the fertilizing regulation. Among the other things, it also covers the use of the biosolids. I mention just the most important regulation, but there are, of course, several which we have to comply. And what can we do to comply with all those regulations? We may try to enhance the anaerobic digestion process, which has basically the four steps which occur one by one. The process is probably perfectly known for you, so maybe it is not necessary to repeat it. However, there is some purpose which I would like to mention, that the steps of the anaerobic digestion are hydrolysis, acidogenesis, and finally the methane genesis. And like all chemical processes which consist from the individual sub-processes, kinetics of the slowest sub-process determines the kinetics of the whole reaction. And in this case, the slowest sub-process is the hydrolysis. So the conclusion is that if we can increase the rate of hydrolysis, then we can increase the whole process of the methane fermentation. And for this purpose, we developed the process which is called thermal hydrolysis. The combination of the thermal hydrolysis and conventional anaerobic digestion gave the process which we called advanced anaerobic digestion. This name was created by the United Kingdom utility company, which holds several water and waste water treatment plants. The company name is Thames Water. And in this case, the sludge is pre-dewatered, and then it is going to the thermal hydrolysis process. The centrate from the pre-dewatering is sent back to the plant, and the hydrolyzed sludge after dilution is sent to the digestion. And as previously, the biogas produced in the digestion process is burned in the cogeneration unit, but it also could be upgraded to the biomethane and loaded to the gas network. The rest of the process is the same. The electricity is produced and heat. The heat is used to produce steam necessary for the thermohydrolysis process. The sludge after digestion is dewatered. The centrate is again sent back to the plant, and as a product, we are receiving the biosolids. Let me now show you how the thermohydrolysis process works. The sludge, it could be a mixed sludge, but it could be separate, for example, only the surplus, is pumped to one of the 4 reactors after the preheating with the recovered steam. And then the sludge is cooked with the steam in the temperature of about 165 degrees Celsius and under about 6 bars pressure. And after that, there is a rapid discharge to the tank, which is called the flash tank. And then there is the rapid depressurization from 6 bars to the atmospheric pressure. So there occurs the process called the steam explosion, which additionally disrupts bigger particles. So this is the advanced anaerobic digestion. This slide already presented to you, and we call it the full Cambi process because it hydrolyzes both the primary sludge and the surplus sludge. But it is not the only solution. There are possible also the other setups of the process where we only hydrolyze the waste activated sludge, and after the pre-dewatering to about 16 to 18% of dry solids, the sludge is hydrolyzed and sent to digestion. Then the primary is added, and this is because the primary sludge fermentate quite well without the thermohydrolysis due to its chemical composition. Then, like previously, we produced the biogas and all the other things. There is no difference to the standard conventional anaerobic digestion. And again, we are receiving as a product the biosolids. The difference is between these two processes that the full Cambi process sterilized the whole sludge before digestion, while the was only process sterilized only the surplus sludge. And so depends on the final disposal of the process, we may use one of the or the other. There is also recently developed the process which is called the intermediate thermohydrolysis, where if we have available digestive volume, we can have the first digestion step followed by the hydrolysis and followed by the second step of digestion. And finally, currently at least, the process which is called the Cambi solid stream. And in this case, the hydrolysis takes place after the digestion, and the centrate from the final dewatering, which consists a lot of COD, which later on can be transferred into the methane, is sent to the first digestion step. This is the comparison of the different processes. The first obvious conclusion is that it reduces the thermohydrolysis reduces the necessary digester volume. And the last two can be used only if there is existing available excessive volume of the digesters. So how the biosolids produced in the advanced anaerobic digestion fits to the circular economy concept. As I already mentioned, the current fertilizing regulation in European Union allows to use the biosolids as the natural fertilizer. But of course, these member states can implement the different regulation. And the example here is Germany, where using biosolids as the fertilizer is forbidden, and only incineration or core incineration is currently allowed. But for example, in the countries out of European Union, like Norway, United Kingdom, USA, Canada, or Australia, the biosolids are commonly used as the biofertilizer. So let's say answer the question how the thermal hydrolysis fits the concept of circular economy. So the first, it stabilizes the sludge already, so no any additional step is necessary. It reduces the volume of the final sludge for disposal. This is because the hydrolyzed sludge is much easier to the water comparing to the conventional process. It hygienizes the sludge because there are no pathogens which can survive such a high temperature and high pressure. And finally, we can recover the energy, energy from the sludge, and reclaim the biosolids and use them as biofertilizer. So last but not least is a tremendous lowering of the carbon footprint. Again, so that's still 2 minutes, so I'm going to the end. The biosolids produced in the advanced anaerobic digestion produces the fertilizer, which is pathogen-free, odor-free, is easy to apply, it's natural, and because it is easy to apply because of the dry solid content in comparison with the sludge which is produced in the conventional anaerobic process. It contains several nutrients which could be successfully returned back to the environment. So that's all from my side. We produce the power from the people and the biofertilizers. So thank you very much for your attention.
Jacek, thank you very much for your presentation. I just checked the slide. No questions to your presentation. I might mention one question. Could you describe a little bit more the market potential of the products you have presented related to the activities of your company?
But you mean the market for the anaerobic digestion process, or the market for the biosolids as the final product?
Biosolids.
As the biosolids.
Yeah.
I must say that, for example, that depends on the country, because, like I said, even if the European regulation allows to use it, allows to use the biosolids as a biofertilizer, there are different internal regulation in each member state. For example, in Poland, about 50% of the sludge is used in agriculture, and partially for the crops for food, and partially for the soil improvement in the forestry, lawns, and this kind of places. In Norway, over 90% of sludge is used in the agriculture and soil improvement processes. In Germany, there, as I said, no sludge is used for this purpose. In European Union, Germany is exception because it is necessary to burn the sludge either in the incineration plants or the cements, power plants, this kind of processes. So another example, we built the advanced anaerobic digestion with thermohydrolysis in Beijing. There are five wastewater treatment plants for the 20 million people, and all of them uses the thermohydrolysis, and all the sludge is used in the agriculture. So there is no simple answer. However, currently the trend is to use the biofertilizers more and more.
Thank you, Emrah. Thank you very much. If there are no other questions, then we can come.
I see there is one question.
Josef
Tregel
has a question, I see.
Sorry, it took me some time to find how to raise hand electronically.
In the electronic way?
Yeah. I just wanted to ask whether have you somehow tried to estimate what proportion of the recycled material or what proportion of the standard, let's say, materials can be substituted by this recycled wastes from the sludge? For example, how much of inorganic phosphorus, which is used as fertilizer very in high quantities, both here and as well as in Poland, can be substituted by the recycled phosphorus from this sludge? Because I don't have the data, but I'm afraid it will not be a high percentage, maybe 10, 20%. The same, for example, for the energy.
Talking about the nutrients, yes, there exist several studies which analyze the necessary amount of the, in this case, nitrogen or phosphorus. I don't remember the exact data by heart right now. However, it is true that there is only some percentage, and in several cases, the addition of other fertilizers is necessary. Typically, the inorganic fertilizer. So I cannot say that it replaces completely the application of inorganic fertilizers, but definitely it reduces the amount of them which are introduced to the environment. If you are interested in detailed studies, so you may just send me an email and I will provide you with some examples of the scientific publication related to this process.
Yeah.
Thank you very much for your answer, Josef. Last question.
I think I can find the literature. I was more likely interested in your personal opinion, especially Poland is in a very agricultural country.
Yeah, that's
use.
The process is, I would say, centrally managed by the Institute of the Soil Improvement and Fertilizing in Puławy in Poland. And they made several studies related to the treated sludge application and issued the certificates and detailed procedure of the implementation. So it depends on the content of the nutrients in the soil, the heavy metals in the soil and heavy metals in the sludge, the content of the nutrients, and so on. So individually, the procedure of application is in detail developed for the particular area of land. And I should say that the demand for sludge, for treated sludge in Poland is so huge that the wastewater treatment plants could produce the maybe 40 or 50% more than it is producing, and the demand from the farmers would be satisfied in this after that.
Okay, I might add the question. The export of sludge from Germany, it's not allowed, it's prohibited.
No, not because we don't want it, but because they don't want to sell it. Yeah. I am very sorry to stop this interesting discussion. Thank you very much. Thank you.
I might say some final words. We had 6 presentations, 6 speakers. They look at the issue of wastewater from different perspectives. So we got really an interdisciplinary picture, interdisciplinary competence. I would like to thank to all speakers especially for the high degree of time discipline. We have still very hard time with online communication, but we managed. I would like to thank organizers, especially Lea Turcarova from the Nordic Chamber, and last but not least to both IT experts in the background. They provided us the comfort of online communication. Thank you very much. I hope see each other next time.
Thank you.